Welcome back to the channel. In the last two episodes, we covered concepts such as measuring non-conformity of a point with a bag of points using, for example, absolute errors, the concept of conformity ladder, where the lower the non-conformity of a point, the higher it sits on the ladder, and also full and split conformal methods and their differences. In the present episode, we will strongly rely on those concepts. So if you have not watched the previous episodes yet, I strongly recommend you do so first. The final goal of this episode, which will be in two parts, is to show how easy it is to add split conformal uncertainty quantification to any model with just a few additional lines of code. But being able to have such an easy and concise implementation requires us to first understand the method in more depth, so we can reformulate it in a way that makes the implementation easy. Gaining that in-depth understanding is the subject of the first part of this episode. Our starting point is a statement that we have seen in the previous two episodes. Given a test or validation point with an unknown label or target value, the 80% prediction interval, that is the interval which has 80% probability of actually containing the true unknown label, consists of all plausible values that, if assigned to the test point, will put it at the top 80% of the conformity ladder. Again, feel free to see the previous two episodes for more details on this. How can we construct such an interval? In other words, how can we program this statement? The first way is obviously to rely on the statement as it appears. That is, to actually try all plausible values one by one. In a regression problem, this will require discretizing the space of plausible values. Then check if a value puts the test point at the top 80% or not. If it does, include that value in the interval. Otherwise, don't. And this is the implementation method I presented in the previous episodes. But there is a more intelligent way of implementing split conformal that does not require trying all plausible values. There are two reasons that allow this, and we are familiar with both of them from the previous episodes. The first one is that with split conformal, we need to fit the model only once. With split conformal, moving the test point the square around to try new plausible values does not require fitting a new model, and that is why in the right plot on the screen, the fitted curve does not change. The second reason is that as the test point moves away from the point predicted by the model, its non-conformity keeps increasing and it keeps moving down in the ladder. In other words, there is a monotonic relation between the distance from the point predicted by the model and the rank in the ladder. These properties of split conformal method and non-conformities allow us to convert the problem of constructing the interval to finding its upper and lower bounds. To better understand this, let's reduce the number of calibration points, the solid dots on the screen, to just a few, for example 4, and make their size proportional to their error. The higher the error of a calibration point, the bigger the size of the dot associated with it. With these modifications, the vertical axis of the non-conformity ladder will consist of 5 subintervals only. Let's call them ranking subintervals and give them names A, B, C, D, and E from the top to bottom. Their corresponding confidence levels are 0.2, 0.4, 0.6, and 0.8. Each of these ranking subintervals corresponds to a subinterval in the horizontal axis. In other words, a range of non-conformities. Let's call them non-conformity subintervals. For example, ranking subinterval A corresponds to non-conformities between 0 and 0.15. Similarly, ranking subinterval E corresponds to non-conformities greater than 0.67. Recall that our non-conformities, that is, the values on the horizontal axis of the ladder, are a function of absolute errors. For simplicity, let's assume they are equal to those errors. So each of the 5 non-conformity subintervals, that is, the horizontal curly brackets, in turn corresponds to a pair of target value subintervals in the xy space, the left plot. To better see this, let's remove the training points. Our test point has x equal to 0.8, represented by the dashed vertical line, and we have a point prediction of y hat equal to about 2.5, represented by the dashed horizontal line. The non-conformity subinterval A corresponds to y values that are less than 0.15 away from the point prediction on either side. You can better see this in the close-up around the point prediction. Similarly, non-conformity subinterval B corresponds to y values that are between 0.15 and 0.31 away from the point prediction, and so on for the non-conformity subintervals C, D, and E. As you can see in the close-up, these y subinterval pairs mirror each other with respect to the point prediction. For example, ranking subinterval A, or equivalently, non-conformity subinterval A, correspond to y values between the point prediction 2.5 plus minus 0.15. This means that a plausible value within that range will lead to a non-conformity less than 0.15 and will put the test point at the ranking subinterval A. Here is the critical point. Due to exchangeability, these subintervals are equiprobable. That is, the probability of the true unknown label for the test falling within any of these y subinterval pairs is equal. Since we have 5 of these pairs here, that probability is 0.2. So a prediction interval consisting of subintervals A, B, C, D, but not E, will have 80% probability of containing the actual test point. In other words, it will be the 80% prediction interval. The y value subintervals A, B, C, and D concatenated together correspond to the top 80% of the conformity ladder. This is why collecting all plausible values that put the test point at the top 80% of the conformity ladder, that is the top 4 non-conformity subintervals, gives the 80% prediction interval. Note that the widths of the prediction intervals we are constructing this way and their corresponding confidence levels are not arbitrary. They are discrete values that are uniquely determined by the non-conformity values and the size of the calibration data set N. In our example, because we have 4 calibration points, these confidence levels can be only 20%, 40%, 60%, or 80%, and nothing else. None of them is, for example, a 70% interval. To properly reflect this, that is, to distinguish these confidence levels from an arbitrary confidence level delta, let's call them intrinsic confidence levels and denote them by delta superscript I, where I stands for intrinsic. Assuming that no point has a duplicate non-conformity score, each calibration point corresponds to one intrinsic confidence level, and we have a relation between the intrinsic confidence levels and the number of the calibration points N, where the subscript J is a counter iterating over the points inside the calibration dataset. In addition, because the non-conformity subintervals are equiprobable, we can view the non-conformity associated with them, that is the non-conformities in our calibration set, as quantiles. Quantiles, as you may already know, are cut points that divide the range of a probability distribution into continuous intervals of equal probability. And the qth quantile, with q between 0 and 1, is a value such that q times 100% of all possible values are below it. In our example, we have 4 quantiles. Let's denote them by q sub 1/4, 2/4, 3/4, and 4/4. There are different notations for quantiles, so it's worth discussing the meaning of the notation I have chosen here. Q sub 4/4 refers to the 4th quantile out of the 4 available ones. In general, our conformity quantiles can be written as Q sub J/N, where again the subscript J is a counter iterating over the points inside the calibration dataset. Thinking about any of the quantiles on the horizontal axis, note how they each correspond to an intrinsic confidence level on the vertical axis. For example, Q sub 1/4 equal to 0.15 corresponds to delta I equal to 0.2. We can express that correspondence mathematically using a relation between the jth conformity quantile, Q sub J/N, and the intrinsic confidence level, delta superscript I. For example, to get the non-conformity quantile corresponding to the intrinsic confidence level, delta I equal to 0.4, simply plug 0.4 to the right-hand side of the equation and recall that N, the number of calibration points, is equal to 4. This will give you Q sub 2/4, which is equal to 0.31. Now that we have understood what intrinsic confidence levels and non-conformity quantiles are, and the relation between them, we are finally ready to derive the easy-to-implement relation for prediction intervals promised at the beginning of the episode. Our interval will be symmetric around the point prediction y hat, where delta y max is the distance between upper or lower bounds and the prediction point. Obviously, that distance is a function of the desired intrinsic confidence level delta I. The higher the confidence level, the higher that distance. So let's rewrite the equation to incorporate this. Next, we need to replace delta Y max with non-conformity quantiles, which we can do by noting that if we insert delta Y max to our non-conformity measuring function S, we will get the corresponding non-conformity quantile. Given an intrinsic confidence level delta I, there is a distance associated with it. Passing that distance to our non-conformity measuring function S gives the corresponding non-conformity quantile. Taking the inverse gives an explicit relation for delta Y max. Let's plug that into the relation for interval. What this equation is telling us is that given a desired intrinsic confidence level, find the non-conformity quantile that corresponds to it, pass it to the inverse of the non-conformity function, and add and subtract the result from the point prediction to get the interval. The coverage probability, that is, the probability of the test point falling within that interval, will be equal to the requested intrinsic confidence level delta I. Let's discuss this in connection with the visualizations we had earlier. Imagine the desired intrinsic confidence level is 0.4. Plugging that into the equation gives quantile equal to 0.31. Passing that to the inverse of the non-conformity function results in some distance. Moving away from the point prediction by that distance covers Y subintervals A and B. And as we have already discussed, from exchangeability, making these subintervals equiprobable, concatenating those two Y subintervals as our predicted interval will result into 40% confidence level. So far, we have assumed that the desired confidence level is one of the intrinsic ones. What should we do when that is not the case? In our example, with only 4 calibration points, imagine somebody requests us to present the 70% prediction interval. That confidence level is not equal to any of the intrinsic ones we have. What should we do then? We have two intrinsic confidence levels, 60% and 80%, and their corresponding widths that surround the desired but not intrinsic level of 70%. Can we, for example, concatenate the bottom half of subinterval D with subintervals A, B, and C and present that as our 70% interval? The answer is no, because doing so would imply that the top and bottom halves of the subinterval D have the same probability of containing the actual test value. But we don't know that. We have no knowledge whatsoever of where within a subinterval the test point is more or less likely to fall. All we know is that different subintervals are equiprobable. So what we need to do is to include the entire subinterval D, which will result in 80% confidence level, even though we are asked for 70% one only. How can we account for this in our equation for interval? We simply need to pick the next higher conformity quantile by modifying the term n plus 1 delta I, which can be done by adding a ceiling to the term. We also remove the superscript I from deltas because that superscript is reserved for intrinsic and not arbitrary confidence levels. This means that our predicted interval will be slightly wider than it would have been had we an intrinsic confidence level equal to the requested one delta. This wider interval, which is undesirable because it increases our uncertainty, is the price we have to pay to not violate the coverage validity. What is the effect of this on the probability of the test point falling within our interval? Think about the y-value subintervals we had earlier and their corresponding coverage probabilities. We discussed that if we are asked for 70% prediction interval, we have to include the entire subinterval D, as opposed to, for example, only half of it, resulting in the actual coverage probability being 80% higher than the requested one. But in general, how much higher that actual probability will be compared to the requested one? Can we think of an upper bound for it? The answer is yes. To see what that upper bound is, let's first make the scene less crowded and focus on subintervals C and D only. Note that the worst will happen when the requested delta is only slightly above one of our intrinsic confidence levels, for example, 60.1%, forcing us to travel away from the point prediction by almost an entire subinterval to reach the next intrinsic confidence level or intrinsic width, because the probability associated with one full subinterval is 1 over n plus 1, as we have n plus 1 equiprobable subintervals, including an entire subinterval, which again is something we need to do when the requested delta is just above an intrinsic confidence level, will increase the coverage probability by 1 over n plus 1. So the requested delta plus 1 over n plus 1 is an upper bound. This is the common upper probability bound that you can find in the literature. But now I will show that we can provide an upper bound that is closer to the lower one, making our relation more precise. As we just discussed, adding 1 over n plus 1 to the requested delta is based on the scenario where delta is only slightly above one of the intrinsic confidence levels we have. In that scenario, reaching the next intrinsic width requires adding almost an entire subinterval, here D. Think about another extreme case. What if delta is just below one of our intrinsic confidence levels? For example, 79.9%. In this new scenario, what does reaching the next intrinsic width, here 80%, require? Does it require us to travel an entire subinterval further away from the point prediction? Doing so will take us above the next intrinsic width. So no, it doesn't. It only requires us to travel further away by a small fraction of a full subinterval, as you can clearly see in the close-up. To take this into account, we need to modify the right-hand side of the inequality. And the new upper bound will always be smaller or equal to the old one, but never greater than it, rendering the new relation more precise than the old one. Let's recap what we learned in this episode. We have an explicit equation for the split conformal intervals. The interval has coverage guarantees, meaning that the probability of the true unknown test value being within the interval is always equal or greater than the requested confidence level delta, even when the size of the calibration set N is small, giving us the nice finite sample validity property. It is also limited by an upper bound that is inversely proportional to N, meaning that the higher that size, the closer the lower and upper bounds, allowing us to become more precise about what the actual probability is. In the second part of this episode, we will see how easy it is to implement this relation, which will allow us to quantify uncertainty of any ML model that provides the point prediction y hat. All we need to do is to calculate a specific non-conformity quantile, input that into the inverse of our non-conformity measuring function, add and subtract the result from y hat. We will discuss this in more detail in the next episode.